Before we continue on with how matrices and systems fit together and are used, we'd be remiss if we didn't at least say, now that we've introduced matrices, are there certain sorts of other basic operations that can be done with them, kind of how we've introduced, numbers and expressions of all different types, and we've said, okay, here's adding, subtracting, multiplying, and dividing. And so let's go ahead and just knock that sort of thing out and take care of the different kinds of matrix operations that we can do. Now, one of the other introductory elements to mention here is that for convenience sake, it's nice to have some sort of shorthand representation for matrices. And we already saw this a little bit with using our calculator for doing those augmented matrices and getting the row echelon form and reduced row echelon form, that in the calculator there was that capital letter for matrix A, matrix B, etc. So using a capital letter, very popular way of being able to work stuff out in a generic fashion. And we can also say with brackets for a matrix and then like a generic little matrix entry. So, hey, here's how you can do things with these matrix entries. And of course, the same sort of thing that we had seen before, where we have like the whole full-blown generic looking matrix, and we don't really want to have to resort to that sort of thing. It becomes a bit of a pain in the rear to take care of some of the things we might want to say. So first of all, a matrix being equal to another matrix, that means basically entry by entry, entry by entry. One matrix entry matches exactly to the corresponding entry in a second matrix. So the first row, fourth column of matrix A is the same as the first row, fourth column of matrix B. That has to happen entry for entry. Matrix addition. We only refer to matrix addition, not subtraction. You'll notice that that doesn't appear here. So matrix addition. We just kind of streamline things and say we add matrices together, and we can deal with subtraction in a clever little twist of a way. But that the matrix addition is basically going to be, for these matrices, we're going to add the corresponding entries. Again, probably not a terribly surprising sort of thing. So adding entry by entry does mean, though, that the matrices we add together have to be the same order, or we also said size, so same size. They have to have the same number of rows and columns in order for that to work. Otherwise, we cannot do the addition. The clever way of taking care of the subtraction is by allowing us to take any regular number, which we can refer to by the word scalar multiplication. We'll take any regular number and multiply it by our matrix. So if we officially wanted to do a matrix subtraction, we would go -1 times that second matrix, and then we'd add. So we turn subtraction into adding a negative. Whatever that means, essentially we're talking about subtraction. But as far as being able to multiply a matrix by a single number, that again is happening entry by entry. Each entry in the matrix gets multiplied by that particular number that we're using. So every entry. Now, let's take a look at a couple of examples here of this stuff actually taking place so that you can get a better feel for what's actually happening here. So these first two already worked out based on matrix A and matrix B. If we do A plus B, we are using first row, first column of A plus first row, first column of B. First row, second column of A plus first row, second column of B, etc., etc. We're adding entry by entry to come up with our answer. 2A. Now we're taking the number 2, we're multiplying it by the matrix A, and officially speaking that means take that number 2, multiply it by each entry in matrix A to come up with your answer. And then this one we're actually going to do 3A minus 4B. Now here's what I was referring to. Officially speaking, we're not going to do subtraction. We're going to rewrite this as adding a negative. So what we're officially going to say is we're going to take 3 times each entry in matrix A. We're going to take a -4 times each entry in matrix B, and we're going to add those entry by entry. Now, what we can really do is just say 3A plus -4 times B, and we'll do that for each entry one at a time using those matrices A and B. 3 times A, 3 times 2 is 6, plus -4 times B, -4 times 0. So I'm literally going to write that in so that we can kind of keep track of what we're calculating here. 3 times the entry from matrix A plus -4 times the entry from matrix B that was in that first row, first column. We can go ahead and simplify that so that we start to build that finalized matrix, that answer. So 3 times 2 is 6 plus 0 is 6. You're welcome to move across the rows or down the columns. Totally up to you. 3 times A plus -4 times B. 3 times 1 plus -4 times -1. So moving across the row and having that entry 3 times 1 plus -4 times -1. So 3 plus 4 is 7. Back up to our matrix A and matrix B, and moving to the second row, first column. 3 times 3 plus -4 times 3 would give us a -3. Moving across that row, 3 times -2 plus -4 times 4 would give us a -22. And moving to the third row, 3 times matrix A plus -4 times matrix B would end up giving us an entry of -12. And finally, 3 times matrix A plus -4 times matrix B would end up giving us an entry of 23. So we have our final answer here for this particular matrix arithmetic problem, 3A minus 4B. We can also do this in the calculator. If we want to take the time of entering matrix A and matrix B, we could then type in 3 times the matrix A minus 4 times the matrix B. If our calculator decided to pitch a fit about the way that was typed in, again, we can rewrite the subtraction as plus a negative times matrix B. So we could type it in this way if our calculator happened to go a little haywire in the first version. 3 times matrix A plus -4 times matrix B. And we should be able to get our calculator to spit that out to us as well. Now, we are going to go back to the calculator here in a little bit because we've got to handle matrix multiplication. And that is a much more involved process. We have some technical comments that we can make about things. And let me just bring those up very quickly to kind of mention them before trying to give you a little bit more straightforward way of thinking about how everything works here with this matrix multiplication. Really the key thing, first of all, is we have to know if we can proceed with the multiplication. So there is one very particular sort of connection that has to take place. The first matrix that shows up in our multiplication problem has to have the number of columns that match up with the number of rows in my second matrix. So A times B. A times B. The number of columns in the first matrix has to match the number of rows in the second matrix. In order for things to work out, that absolutely positively has to happen. If those two numbers do not match up, like writing the sizes, the orders of those matrices, if you write them 3 by 4, 2 by 3, when those interior numbers don't match up, the matrix multiplication cannot take place. 3 by 3 times 3 by 8. That matrix multiplication can take place because those interior numbers would match up. That's something we absolutely need to pick up on. Now, if those interior numbers match up, the number of columns from my first matrix match up with the number of rows from my second matrix, if that matches up, then we've got a technical comment here, and frankly, nobody likes to want to really decipher that sort of thing unless they're totally jazzed about matrices. So it's a lot easier for me to try to do something a little along the lines of this. I'm going to show you an example here and try to kind of give you a little description of what's happening. Matrix A, matrix B, the number of columns in matrix A matches with the number of rows in matrix B. This will take place. This matrix multiplication will take place. Now, coming out of that, and this is a little easier to talk about with an example, those outer parts of my sizes will end up giving me the size for my answer. So the number of rows in matrix A and the number of columns in matrix B will actually tell me how big my answer is. The actual process, though, again, this is the weird kind of squirrely part. What we're going to do is we're going to take a row from the first matrix. So this is circled in dark blue. And we're going to take the columns from that second matrix. So we're going to do a row. We're going to do the columns. We're going to fold these together. It's kind of like a little shuffling effect. So first row, first column. What we're going to do is we're going to shuffle those together and condense them down into an entry, one entry. First row, first column gives me first row, first column entry in that product. 2 times 4 plus 3 times -1. I'm taking these and kind of shuffling them together and then condensing them down into that entry. So the color coding here trying to indicate how we're putting things together. Notice that there's some common things that show up as we look at one row at a time or as we look at one column at a time. So let's kind of make some of these handy comments here. First row of matrix A is half of what we need for each entry in the first row of our answer. The second row from matrix A is half of what we need in the second row of our answer. The third row from matrix A is half of what we need in the third row of our answer. Now that takes care of half of the work. That kind of gives me a way of filling out half of the calculations that I need to work through. Excuse me. The other half is going to come from the columns of my matrix B. So the first column of matrix B gets filled into the first column of my answer. The second column of matrix B gets filled into the second column in my answer. The third column of matrix B gets filled into that third column in my answer. And so this gives me kind of a nice little way of trying to put together all of these individual calculations, and I can now figure out each one at a time and come up with those entries that I need. Let me show you what I'm talking about. So, we're going to use the same matrices. They're up on the top. They're repeated here as well, just to make things a little easier on ourselves. And again, I've circled things with some color coding to try to help things along for making sure everything works out. Now again, we want to make sure first of all that we're allowed to do the multiplication, and we would want to have an idea of how big our answer is going to be. So the size that we would have for the first matrix now is matrix B. That is a 2 by 3 matrix. The second matrix is matrix A, and matrix A is a 3 by 2 matrix. And that means that this multiplication can take place. The answer for this B times A is going to come from those outer parts of the size, the order, the 2 at the very, very front, and the 2 at the very, very end. So this is a 2 by 2 matrix. Let's go ahead and open up our matrix bracket here. And so the first row of the first matrix is going to inform the first row of my answer. So my answer is going to partly have a 4 blank plus 2 blank plus 1 blank, and then that's just for the first entry. I'm going to repeat exactly that same little setup here for the other row entry here. So repeating exactly that same thing. Then I'm going to go ahead and do the second row business, where we've got this aqua kind of color going on, and that's going to be a -1 blank, 0 blank, 3 blank, and then I'm going to repeat exactly that same thing in the other entry in this second row. That takes care of half of all the calculation work that I've got to do. But I need to fill in the blanks that appear after each of these pink and aqua numbers. So those are going to come from my second matrix, and those are going to be based on columns. So I've got this dark red going on here that I am going to use, and that dark red set of numbers is going to be filled in along the first column in my answer. So that means a dark red 2, a dark red -1, and a dark red 0. And then those are going to go immediately underneath as well, because again, those are filling in the blanks for my first column. So ba-bam, there's those entries getting filled in. So it's this little kind of shuffling sort of idea happening here, and the second column numbers would be going into the other set of blanks over here in my second column with the 3, the 1, and the -2, and right underneath those again 3, the 1, and the -2. So now I've got a string of calculations to work through to get my 2 by 2 matrix answer. And if we go ahead and work that out, 4 times 2 is 8, plus -2 plus 0. 8 plus -2 is 6. Again, you can move across or down. We did across before. Let's move down here. -1 times 2, -2, 0, 0. Oh, so a -2 down there. 4 times 3 is 12, plus 2, minus 2. So a 12 there in that entry. And then last, -1 times 3, 0, 3 times -2. So we're going to get a -9 for that. Now it would be a whole lot nicer for us to be able to actually take the time on our calculator to check something like this. With so much more involved in this particular process, there's a lot more room for error, so having that calculator as a backup to make sure that we did things correctly is a wonderful sort of thing. But there's something else, and hopefully this has kind of popped out to you as a little bit obvious. We did the first version of multiplying where the A came first and the B came second, and that gave us a 3 by 3 matrix. And then here we've just completed the B times A, so matrix B comes first, matrix A comes second, and this is a completely different size matrix. So unlike other multiplying that we've seen before, for instance, 3 times 4 is the same as 4 times 3. Where the order didn't matter, we still got the same answer. Now, that is very much not true anymore. It may work out sometimes that A times B is equal to B times A, but it doesn't happen all the time. So sadly, we don't have that nice sort of situation going on where the multiplication works out as, let's see, I'm so unused to using the official jargon here, I think that it's commutative, that it's not going to work out the same, A times B, B times A. There's no guarantee about that any longer. Bummer. All the more reason to be careful. Because again, this is a bit more of a challenging sort of thing to work through if we do this by hand, if we have to work through and show our steps for this. Let's go ahead and do one other set of examples of the multiplication problems and check things out. So again, the first part that we're going to be looking at is the size to make sure that the multiplication can take place. So matrix C is a 3 by 2, and matrix D is a 4 by 3. In order for that multiplication to take place, those two inside numbers have to be the same. And they're not here. Meaning that C times D cannot be done. So, at least there's that. D times C, well, different story. We're going to have to check out the size here. So first of all, now D comes first, so that means 4 by 3 times matrix C, which is a 3 by 2. And so this does mean that we can multiply D times C, and it is going to be, based on those outer values, a 4 by 2 matrix. So D, let's go ahead and rewrite that, and then we'll write C beside it. And once we do this by hand, we can come back to the calculator work and verify the answer. So, 4 by 2. We'll make sure that we've got enough room to write things down. And let's go ahead and let's do the color coding kind of as we roll through. So we'll go ahead and we'll start with the first row. of matrix D. That means that in our first row, we're going to have a 4 blank, 0 blank, 1 blank. And then we're going to have that exact same thing repeated again over across in that second column of our first row, like so. Basically, now I'm going to do the same thing with the other rows. So -1 blank, 1 blank, -1 blank, and then repeat that again off to the side in my next column. Third row, again, same sort of setup, 3 blank, 1 blank, 0 blank, repeat, 3 blank, 1 blank, 0 blank, and then one more row to take care of, a 2 blank, a 1 blank, and a 2 blank, and then repeat that across. Again, that's half of what we need. The other half is going to come from the columns of our matrix C. So, first column of matrix C in the aqua color now gets filled in the blanks that show up in the first column of our answer. So 3, -1, -1, filling in those blanks, and then those are just going to carry down that column. So filling those in. And then, same sort of idea with the other column of my matrix C, moving over to the other column in my answer and filling in those empty blanks, -1, +1, +3, and then again, down the columns, down that second column, down that second column, that goes ahead and finishes up the listing of calculations that we've got to perform. Now we can go ahead and go through each of those. 12, 0, -1, -4, 0, 3, -3, -1, +1, +1, +1, -3, 9, -1, 0, -3, +1, 0, -6, -1, -2, -2, +1, +6, so provided I didn't get too cocky about working through those so quickly, this should be our answer. But again, we're going to go ahead and take matrix D and matrix C. We're going to enter those in the calculator, and we're going to tell the calculator do D times C. and then we can see how that works out. So I'm going to flip-flop back and forth between the calculator and this particular screen so that I can enter those matrices. And I want to, in my calculator, bring up my matrix menu, and then I'm going to want to edit. Let's use the same names so that we'll go ahead and scroll down to matrix C. We'll hit enter. We're going to want to change the size of matrix C so that it would be a 3 by 2. That will automatically change the appearance on the screen so that there are those 3 rows and 2 columns. So we need a 3, -1, 3, enter, -1, enter. In the next row, a -1, +1. So -1, enter, +1, enter. Then we need a -1, +3. So -1, enter, 3, enter. And there's our matrix C. So that is good to go. We will go ahead and get out of matrix C, go back to our matrix menu, go back to the editing feature, scroll down to matrix D, and enter that. That is actually already set up in the appropriate size, 4 by 3. And that, I wonder if that's actually already the matrix D that we've got in this example. 4, 0, 1, yep. -1, 1, -1. Sweet. 3, 1, 0, yep. And 2, 1, -2. Oops. I didn't actually do a 2, 1, -2. So I'm going to fix that so that it matches with the work that we've already gone through to do. And we're just going to go ahead and hit enter along the way. And I think we can actually scroll down. Yeah, we certainly can. So that's going to be 2, 1, 2 along that bottom row of matrix D. That way it matches up with all the work that we spent time doing by hand. Oh, heavens to Betsy, I would not want to have messed that one up. So, lucky me, I get to just change the example that we did that way. So now matrix D times matrix C. Let's go ahead and do that. So back to our matrix menu, and we want to select the matrix D, and then times, and then back to the matrix menu again to select matrix C, and we're going to hit enter. And there we go. We've got 11, -1. Check. We've got a -3, -1 in the second row. Check. We've got an 8, -2 in the third row. Check. And we've got a 3, 5 in the last row. That is also check. While we're here and while we've got those particular matrices, let me go ahead and show you what would happen if you had willy-nilly tried to do C times D, so that you can kind of get an idea that even the calculator should be programmed to error. Dim referring to dimension mismatch. They are actually telling you that the dimensions, the size, the order of those matrices does not match up properly to actually compute that product, to do the multiplication. So even the calculator will try to catch you if you're just kind of checking things out with the calculator based on what you might have already done by hand. So we've got those, and again, just to be responsible, we wanted to hit those ideas. We do have the idea of, let's not say division, but we have what we call an inverse matrix. And we're going to talk about that separately because that ends up being useful to us in terms of going back to systems of equations and trying to solve systems. So we kind of save that for something else in a separate video and just kind of say, all right, we've hit most of the arithmetic here, and the arithmetic that we've got going on, the adding ideas, all right, we can do them. They're not going to really be super helpful to us in terms of systems, but the matrix multiplication will be. So that matrix multiplication will actually be carrying along with us to use in another little bit. when we go back to connecting systems and matrices together.